So welcome back to Chemical Kinetics. Today we are going to look at the procedure for obtaining the rate law from an experimental data. This is also sometimes called the method of initial rates. In questions like these, you will always be given a balanced chemical equation and a table of data, which usually has the word trial or experiment. So here you have trial 1, 2, 3. Then you're given the concentration of the first reactant and the concentration of the second, third, as many reactants as you have, and the experimentally determined rate in each trial is also given to you. So that's the data, and then you're asked to find the rate law. Sometimes you're also asked to find the rate constant and the units of K. Now keep in mind that the rate law cannot directly be written from the balanced chemical equation. It is always experimentally determined. So you begin by writing the statement, let the rate law be rate equals K times concentration of the first reactant raised to power M, concentration of second reactant raised to power N. So the easiest way to do this is to pick two trial options where the concentration of one reactant is changing, but the concentration of the other reactant is staying the same. Later on, you will see that that is not always necessary. It is possible to figure out the rate law even without that. But to begin with, that's a good place to start. In this case, we observe that the concentration of ClO2 is staying the same in trial 1 and trial 2, whereas the concentration of fluorine is changing in these two trials. So what we are going to do is write down a ratio between trial 1 and trial 2, and then make a ratio between rate 1 and rate 2. And now if we did plug in the rate law here, you don't have to write this part out explicitly on your test. I'm just writing this here to show you. And then I realized the mistake. It should be ClO2 up there. So you're basically just plugging in the concentrations of fluorine and ClO2 in trial 1 and in trial 2 in your ratio. So let's go ahead and put in those numbers, 0.01 raised to power n, 0.01 raised to power n in both cases because it's not changing. And the concentration of fluorine is changing from 0.10 to 0.20 in trial 2. Remember, K stays the same because K only depends on temperature. It does not depend on concentration. So do not write K1, K2. Let me now go in and plug in the rate values experimentally determined, rate 1 and rate 2. Now I'm going to solve this equation for M. I see that I can cancel out most of these terms. So what is left is 1/2 equals 0.10 over 0.20 whole raised to the power M, which is nothing but half raised to the power M. And the only value of M that makes this equation true is when M equals 1. Now let's go back and solve for N. So again, I am going to look for two trials where the concentration of fluorine is staying the same this time and the concentration of ClO2 is changing. So this is what you write on a test. You just write trial 1, trial 3, you plug in the values for the rates, and you don't need to write the rate law again and again. You can simply plug in the values for the concentrations of the reactants as given. So in this case, K times 0.10 raised to power M, 0.01 raised to the power N, and then the same idea with trial 3. We plug in the concentration of fluorine that is staying the same and the new concentration of ClO2. To solve the equation, we cancel out the things that can be removed, and we get 1/4 equals 1/4 raised to the power n. And we know that the only value for n that satisfies that equation is when n equals 1. So we've solved m and n. In order to solve for k, let's bring back the rate law, which is, again, you don't need to write the rate law explicitly here, but just to show you that we have already figured out the rate, we know the concentration of fluorine, concentration of ClO2, and the values of M and N. So we sub all these known variables from any one trial. And I'm picking trial 1. You could pick any one you like. You sub in all of these known variables to solve for K. So I get K as 1.2. Notice that there are no units to K here. So let's go back and try to find the units for K. I haven't left a lot of space for myself, so I'm going to move this here. Now, since you have already figured out the order with respect to fluorine and the order with respect to chlorine dioxide, we know that the overall order is 2. So this is a second order reaction. Either you remember the units of K for a second order reaction, or you can calculate them as before. So write the units for rate, which are always moles per liter per second, but that's also given to you in the question itself. Units of K, and because it's a second order reaction, I am raising concentration to the power of 2. So using dimensional analysis, I bring all the other units to one side, and I can cancel out the liters and the 1 moles. So that gives me the unit of K as liters per mole per second. Now you finally end this by writing a statement. Therefore, the rate law is rate equals 1.2 F2 raised to power 1 ClO2 raised to power 1. Notice that we don't actually explicitly write the numbers 1. Now, there is some disagreement on this. Most textbooks or teachers will also accept the answer rate equals K times F2 raised to power 1 ClO2 raised to power 1. These are both acceptable. Figure out what your teacher wants. For the AP exam in general, when they say find the rate law, they will accept rate with just K. And then if they want you to find the rate constant, they explicitly ask you the question, find the rate constant and the units of K. So this is one way of answering a question like this. Let us look at another way you could do this as well. So that solution would be written in words. You would write from trial 1 to trial 2, I noticed that ClO2 concentration is staying the same, but the concentration of fluorine is doubled. At the same time, I noticed that the rate is doubled. Therefore, the reaction must be first order with respect to F2. And then you write in words again from trial 1 and trial 3, the concentration of fluorine stays the same, but the concentration of chlorine dioxide is getting quadrupled, and I noticed that the rate is also being multiplied by 4. Therefore, the reaction must be first order with respect to ClO2 as well. And then you can write the rate law. Rate equals K times F2 raised to power 1 ClO2 raised to power 1. We do not write those implied ones, and that's the rate law. The procedure for finding the value of the rate constant, the units of K will stay the same. So it is your choice if you want to answer this in words or if you want to answer this mathematically. The only difference is that your answer in words would mostly only work if you could right away see how the rate is changing. So if it's not a whole number or if it's not easily visible, then you would have to do the mathematical treatment. Now let's look at a question which you will need to use the mathematical method for. It is not possible to simply look at this problem and right away see if the reaction is first or second order with respect to any of the reactants. So let's take a moment and read the question. So the question says, the rate of the reaction between hemoglobin, Hb, and carbon monoxide was studied at 20 degrees Celsius. The following data were collected with all concentration units in micromoles per liter. So a micro is 10 to the minus 6. So micromoles will be 10 to the minus 6 moles, and moles per liter is the concentration. So here is the data given to us. What do we notice? That as the concentration of hemoglobin is doubled, what happens, and the concentration of carbon monoxide is kept constant, Well, the rate is not exactly double, is it? If it was exactly double, we could have said that the order with respect to hemoglobin was 1. So in this case, we need the mathematical treatment. Let's start with writing our assumption that let the rate law be rate equals K times hemoglobin raised concentration of hemoglobin raised to the power of m, concentration of carbon monoxide raised to the power n. And then picking my trial 1, trial 2, hopefully you will practice enough of these questions that this part becomes easy enough for you. So let's plug in all the values. I can cancel out things that are the same. That gives me this number 0.519 over 1.44 is equal to 1 half raised to the power of m. In order to solve something like this, we need to take log of both sides. So I say log of this whole fraction in here, and then using the rules of log, I can write m times log 1 half. So to solve for m, let me isolate m, move everything else onto the other side. And I need a calculator, so I get m as 1.472. And because I have 3 sig figs in the numbers that are given to me in the question, let me write the order in 3 sig figs. So I get the order as m equals 1.47. To solve for n, I write the same thing. I go trial 2, trial 3 this time. And I write the rates for both the trials, but then I just noticed that the last time I had left out those micromoles 10 to the minus 6 in all those other quantities. Now, because they are both being raised to the same power, m and n, it will always cancel out, it doesn't matter. The only place that this 10 to the minus 6 can introduce an error is when we are calculating the rate constant. So just be careful of that. Now, in order to be precise, let me correct my error the first time and let me write down 10 to the minus 6 value when solving for n. Hopefully this hasn't confused you too much. So plugging in the correct values, double checking for any errors, found one. So again, simplifying this and taking the log on both sides, I get log of 1.44 over 3.71 is n times log 1/3. Using my calculator to solve for n, I get n as 0.861 as the order with respect to carbon monoxide. So I can combine both of these informations and write the rate law as rate equals K times concentration of hemoglobin raised to 1.47, concentration of carbon monoxide raised to 0.861. If you were asked to find the overall order, you could just add those numbers together. To find K, let us sub Mn in any one trial of your choice. I will pick trial 1. So let me plug in the values here from the table. So rate is 0.519 into 10 to the minus 6 equals K times the concentration of hemoglobin 2.21 into 10 to the minus 6 raised to the power 1.47 times concentration of carbon monoxide raised to 0.861, bringing everything else to one side and isolating for K, I get K equals 1.57 into 10 to the 7.